Alright everyone, welcome. My name is Stefan Tan and welcome back to another educational video. Today we have an introduction into statistics, and this will be taught from an IB student's point of view. I remember taking statistics in Math SL and it is not too challenging, but one of the best things about statistics is that outside from school there are many implications, especially in our future occupations. Whether you be a teacher or an engineer or a pilot, statistics will always come in handy, and there are many subtopics within statistics that are also widely used throughout an individual's lifetime. So it is very important to gain a strong understanding of the concepts of statistics, when to use them, how to use them, and also the implications of statistics in many different real-life situations. Now, to begin, I'd like to introduce three quotes that I found intriguing. The first is from Andrew Lang, who is a Scottish poet, and his quote is, "Most people use statistics like a drunk man uses a lamppost, more for support than illumination." Now, this use of simile to me is it's interesting because, you know, you think of a drunk man and a lamppost and he's just using it for like support, right? And he's saying how that is similar to statistics. So for Andrew Lang, statistics is a method for supporting a fact more than illuminating or finding a fantastic new discovery into something. It is more used for an element of support, to support one's claim, to support one's argument, rather than to feel some form of breakthrough in terms of development. So that's for Andrew Lang. Next we have Ernest Rutherford, which is a well-renowned New Zealand physicist, and his quote is, "If your experiment needs a statistician, you need a better experiment," right? And it makes some sense. It may or may not make some sense to us. However, for me, I interpret this as saying that an experiment has to have obviously a purpose, and there has to have forms of calculations involving the errors, uncertainties. There has to be repeated trials, and a statistician most likely will use data, whether if it's scientific, mathematical, or if it's just for data collection. They often will have to process the data and will have to infer and interpret the data like any scientist does. But if there's a need for a statistician behind it, then that means that either the experiment is not thorough enough or there is some guesswork involved, and that might be what Ernest Rutherford was implying when he made that quote. And finally, from Benjamin Disraeli, former Prime Minister of the United Kingdom, and he states that there are three types of lies: lies, damn lies, and statistics. So for him, he's viewed statistics from a different point of view, and he has claimed that statistics can be used as a form of lying in some sense. And sure, there are also some negative implications to statistics. There are definitely disadvantages in using statistics, and also the misuse and the risks of using statistics, misunderstandings, miscalculations. There are definitely negative implications to it, and maybe to Benjamin Disraeli, that was one of the impacts that he had to deal with, the disadvantages of statistics. But nonetheless, I hope these three quotes has given you some insight into how statistics are used, whether if you are a poet, if you are a physicist, or you are a politician. Statistics, as I've previously mentioned, plays a huge part in many lives and is continued to be used throughout an individual's lifetime. So moving on, we have the table of contents, and I will move through all of these topics methodically and systematically. I will start off with what is statistics, so the big idea, the definition, the types and the purpose of statistics, the difference between statistics and probability, so some real-life applications as well as a personal example, and finally the strengths and the weaknesses of statistics, namely the advantages and disadvantages. Then I will move through the main ideas, types of distributions, the sample methods, or sampling methods rather, the correlation and how to find outliers, scatter plots and histograms. These are all methods of visualizing data, cumulative frequency, as well as standard deviation and variance, before moving on to box and whisker plot, which is another form of visualization. And then finally, we have the closing points, and I'll provide some additional reading material if any individuals watching this video would like to research more about statistics to gain a better understanding, a more in-depth understanding, more complex understanding of statistics before my final slide, which is the works cited page. So let's start off with, what are statistics? So to define statistics, I've searched up two definitions, one from the Cambridge Dictionary and a second from the Oxford Dictionary. So the first definition is from Cambridge Dictionary and defined it as a collection of numerical facts or measurements as about people, business conditions, or weather. And Oxford Dictionary has defined it as the practice or science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring proportions in a whole from those in a representative sample. You can observe that I have bolded some important words for me personally. I think that collection, numerical facts, measurements, collecting, analyzing, inferring proportions, representative sample are all keywords that one should familiarize themselves with. Statistics, when we think about statistics, we want to think about collecting the data, how we organize the data, how we present the data, and how the data is interpreted also, because many of the times statisticians have to present data and to visualize data in a way that us everyday people, the public for example, will be able to interpret it without any misconceptions or misunderstanding. And oftentimes this data deals with numerical facts or measurements, and there's a lot of analysis and sometimes even inferring that is present when interpreting this sort of data. So it is important for us to think about these ideas as we leisure on our way through statistics. Moving on, we have the types and the purpose. So there are two types of statistics. There is the descriptive statistics as well as the inferential statistics, which you can probably tell which is which. Descriptive statistics deals with descriptions and inferential statistics deals with inferring and analyzing. So descriptive statistics, it focuses on the central tendency, which represents the central point or typical value of a data set, which in other words can be named as the average, or where most data converge or most data is present within a data set. Variability, which measures the spread or dispersion in a set of data, which allows comparisons to be made with other data, and tools such as knowing the range, the variance, and the standard deviation, which we'll talk about in a few slides, will help us to determine the variability. And when you think of variability, you think about variety, right? But in terms of statistics, variability simply refers to how spread out the data is, whether if there are clumps of data points or data values within a graph or if they're all spread out, that is variability. And the distribution of sample data. So when we think about distribution, you want to think about the shape that is presented by the data, and this is often represented by histograms or dot plots, which we'll talk about in a few slides as well. So you want to think about the shape. We've learned about linear functions, maybe we have learned about exponential functions, right? And there are different shapes that go with these in terms of the line that's being created. But for example, when data is being visualized on a graph of some sort, sometimes there aren't any lines that are present on the lines. They're simply plots, right? Coordinates, x, y coordinates on the graph. However, sometimes statisticians and even ourselves are able to visually comment on what type of shape the graph makes, and being able to comment on this shape and considering what two observed characteristics are being compared, we can sometimes be able to comment on the implication of the shape and what the shape on the graph means. So that is what we should be thinking about when we think about the distribution of a graph. And finally, it helps to describe differences between observed characteristics, or simply observed characteristics meaning different, whether you have your control or your variable, of the elements of a data set. So that's for descriptive statistics. For inferential statistics, it is being able to draw conclusions by extending, or in other words, extrapolating beyond the presented data alone, and sometimes even interpolating. So extrapolating, you think of extra. So within the data set, maybe your range is from 0 to 10 and you want to extrapolate, so you want to go beyond 10. And interpolating, it is going within the 0 to 10 range. So maybe you will interpolate within the data of 0 to 10, you might go to 5 to 4 to 3. It is called interpolating. And that has to do with the shape or the distribution of the data set. Also making judgments on the probability, and in this case you can think of the possibility of an observed difference between groups is either dependent, a causation, or a phenomenon due to pure chance. So inferential statistics, you want to think about analysis, right? When there are two observed characteristics being compared, maybe you're comparing X and Y, an apple to an orange, for example, or in a real life situation, you might think of the age of an individual compared to their overall wealth that they have accumulated in their lifetime. Then you might want to find out whether if money, wealth, is dependent on the age, whether if wealth is a causation due to age, or whether if this phenomenon where older individuals have more money is just due to pure chance. Is making that judgment how possible, if it's a plausible possibility that this is dependent on another factor, if it's a causation of a factor, or whether if this is simply a phenomenon due to pure chance. That is something that inferential statistics will deal with. It also is able to make inferences from data to generate general implications. So for example, with the previous example, we have how older individuals, or as individuals age, they will have accumulated a greater amount of wealth. Then maybe we can generate a general implication saying that the older an individual becomes, then the richer they become, or the more money they have accumulated. That could be a general implication, some kind of statement at the end to conclude what you have found out. That is a general implication. In terms of inferential statistics, it can also help us with testing hypotheses, which is a more complex task in terms of the statistical realm in mathematics, but it is of great importance for testing hypothesis. Inferential statistics is. Finally, inferential statistics aims to use random and unbiased sampling methods. So that is important as statisticians to collect data that is random and also unbiased. Otherwise, the data is either unreliable, unprecise, inaccurate, and these are all potential problems behind not being unbiased when sampling. But we will talk about what sampling means and the different types of sampling method very soon. So for statistics and probability, these two terms, although they're similar, have unique differences to them. Sometimes people use these two terms interchangeably as if they are synonyms of one another. For me, statistics and probability are two individual bodies of mathematics. They are very different, but they do depend on one another in many scenarios. So for statistics, it is a branch of mathematics that concerns with the collection, organization, presentation, and interpretation of data. So statistics is more of the bulk work, right? It's collecting the data, it is organizing it, being able to present it or visualize it, and then interpreting the data. Whereas in probability, it concerns with the likelihood. So what's the possibility of something happening, of an event occurring, often with the aid of numerical descriptions. So you can see in statistics, there isn't much information that is being presented in terms of numerical data. That is the work of a statistician to find that numerical data. You're being provided descriptions in terms of like descriptive information. Whereas in probability, you're provided descriptive information, but you're also being provided some form of statistics in terms of numerical facts. So statistics and probability, they're similar in many ways, and probability does depend on statistics at times, and statistics does depend on probability in other less likely scenarios. But these two bodies of mathematics are still unique, and we must define them individually, but understand the similarities and differences between them. And do note that the probability is often used to evaluate short to medium-term events, whereas statistics is often used in medium to long-term scenarios. And this all has to do with the advantages and the disadvantages of statistics, why probability is used for short and medium term, and statistics is used in medium to long term. It's all due to the reliability of statistics as well as the time frame that's provided for making a decision using probability or making a decision or reasoning through statistics. And probability employs reason with previously collected data, whereas statistics is the collection and the processing of raw data. So if that is a way for you to remember the differences between the two, just remember that probability employs reason with previously collected data, employs reason through descriptions perhaps, and statistics is more of the bulk work. It is the collecting, organizing, and the visualization, as well as the interpretation of data, which is all included in the processing of raw data. So we move on to the real life applications. So the purpose of this slide is to simply elaborate on the importance and the implications of statistics, because some of us, maybe in chemistry, in physics, in mathematics, sometimes we complain about, like, what are we going to do with all this mathematical knowledge, right? Why do we have to learn about the quadratic equation? Why do we need to find, for example, the normal line or the tangential force in physics? Why do we need to learn this and learn that? Well, statistics is, as I've said in the past, is extremely crucial in many of our day-to-day activities. And this slide just serves to show some implications, some real-life situations on a local, national, and international level. So for example, you're at your school and you are being asked to sell at your cafeteria, sell some products, right? You have a total of a budget of $10, for example, right? And you can either buy 15 Kit Kats, or maybe sneaker bars is another popular choice for many, right? Or you can buy 10 sneakers, right? Let's just say 10 sneakers, 10 S's represents sneakers. And you want to know which product can sell you more. Either you have your 15 Kit Kats that can sell you, give you the most amount of profit, or whether your 10 sneakers are going to help you to gain the most amount of profit, right? So how do you go about this? A statistician will conduct a survey, right? They will maybe survey 10 or 15 people or 30, 40 people in the school, and to see what is the ratio of people that like sneakers more compared to people that prefer Kit Kats. And maybe they find out that, for example, in a pie graph, in a pie chart, they find out that maybe 33% of people prefer Kit Kats, and maybe 66% of people prefer to have sneakers, right? So then now, knowing that there's about 66% that prefer sneakers, well then the decision made is most likely going to be sneakers, right? This is the better option to select, and maybe you will spend $10 on 10 sneakers instead of 15 Kit Kats, because you know that your 10 sneakers is the preferred snack, right? So that could be a local implication. On a national level, that could be collecting sample data of students' academic success in terms of like the percentage per province, and maybe the government is offering a nationwide scholarship to students from the highest overall mean percentage. And how would you find that? Well, would you survey students from each school? Well, that might take a long time, right, on a national level. So maybe the Ministry of Education from each province might have data stored in your database, and they will find the average or the mean percentage per province. And maybe BC has the highest. Maybe BC, the average percentage in terms of academic success, maybe in grade 12, is equal to maybe 96%. So students score an average of 96% in their grade 12 year, right? So that could be on a national level, right? That's an application of statistics. And on an international level, maybe this is presenting data on the increasing infection and death rates of infectives due to the COVID-19 vaccine in relation to the rate of vaccine rollouts worldwide, right? So maybe you can create one graph to show maybe overall you have, this is the death, and this is time, and maybe the death rate due to COVID-19. You can see maybe it is increased exponentially and then it comes down a little bit and goes up and down, and you're able to find out these trends, what are the maximums, right? What are the hitches in the death rates, and you can maybe comment on why these are happening, right? This could be something, and then maybe you create the World Health Organization creates another graph, and this is maybe the vaccines over time, the vaccine rollout over time, and maybe it's slow, and then goes up a little bit, it goes up a little bit, and then more and more companies start to invest into vaccine rollouts, and it goes all the way up, and then slowly comes down a little bit, it plateaus, and then we can evaluate at each instantaneous point, for example, compared to these hitches, whether if there are trends showing that if there is a greater increase in vaccine rollout, whether if there are less deaths, or if there's a decrease in infections. That could be something that we can think about. So this is an application on an international level, right? So we can see how statistics is crucial on a local, national, and international level. And those are just three small examples. There's so many, there's a multitude of examples available from our day-to-day lives. And statistics, whether we recognize it or not, whether we observe it or not in our daily lives, it is always present. And something as simple as counting could be a form of statistics. Statistics is beautiful in that sense, but we must acknowledge it in our daily lives to really appreciate how important it really is. So this is my personal example that I've included in my TOK essay, and it is that Google DeepMind's AlphaGo actually was able to win 4 out of 5 games against the 9-dan Go master, Go being a popular board game involving black and white stones, which is popular in countries like China and Korea, and increasingly other countries around the world. And there's this Go master, Lee Sedol, and he is actually a 9-dan Go master, which is one of the highest levels of Go. And he has had decades of Go experience. And at that time, I think it was a few years ago, there were a lot of critics against Google saying that Google will not be able to win the 9-dan Go master Lee Sedol because machine learning and AI and statistics and algorithms are not capable of defeating a human with human experience, with over a decade or 2 decades of experience, human experience, right? But contrary to that, that was actually not the case. And in fact, Lee Sedol lost 4 out of 5 games against AlphaGo. And AlphaGo is a self-learning AI that uses an algorithm to analyze past games, and using both probability and statistics. Once again, you can see how they're different, but we have also discussed how they are dependent. They can be dependent on one another or used simultaneously. And in this case, AlphaGo was able to use both probability, evaluating the probability of Lee Sedol's move on every instantaneous move in the match, and using statistics to compare the rate of success per each move, such that the algorithm was able to generate up to 50 moves ahead and evaluate the probability of winning a game using that move from a wide permutation of moves. So that is another that could be another international real-life application, and one of such that is very interesting to me, especially now we're becoming a more technologically advanced and technologically savvy civilization and generation. It is important to understand the importance of statistics and probability in terms of aiding our everyday decisions and allowing us to progress forward as a civilization. So in terms of the strengths and the weaknesses, there are, of course, for almost everything in the world, whether it be from technology or some form of healthcare or even a politician or favorite football player, there are always advantages and disadvantages to that sort, right? So starting off with the advantages. So what are the advantages of statistics? Well, the advantages of statistics include how patterns and correlations can be visualized to establish generalizations as well as relationships, right? So you can see how patterns and correlations, right? Those are two different words, but patterns, you think of it as, for example, you can see there's 1, 2, 3, 1, 2, 3, 1, 2, 3. That could be a pattern, right? And correlation, that we will get into what correlation means in a few slides, but correlation, you want to think about being able to draw some form of conclusion about a set of data, right? And usually correlations they go in hand with patterns. So if you can see, there's there's some sort of pattern in a data set, then you might be able to come up with a correlation based on that pattern, right? And that's always dealing with how data is being visualized to establish generalizations. So we said just now, generalizations are maybe simple sentences or a statement about the correlation due to the patterns. So generalizations is being able to generalize what this data means and the larger picture behind what this data represents. And also relationship, it can be cost effective and time efficient, right? Cost effective and time efficient, I think those are two of the most important things, especially today when we are during the COVID-19 pandemic. We don't have a lot of time to waste, right? Especially in terms of collecting data. So being able to collect data and to analyze it using past data and present data is definitely a large tool and an upside into why statistics is very important. And also in terms of cutting down time, smaller samples can be used to represent population data, right? We'll get into what samples and what population means, right? When we think about population, we think about the entirety, what encapsulates something. We think about samples, we go to Costco, before we buy maybe a pack of nuts, or before we want to buy a carton of milk, we might want to test it out. We can, consume some samples and decide whether if we like that product or not. Well, in statistics, it's very similar. You collect smaller samples to generalize it to the rest of the population. And so smaller samples, instead of having to survey 10 million people, we can survey maybe 50 or 60 people, and finding generalizations and patterns within that population or within that sample, we can actually extrapolate that to represent the population. So that is an advantage of statistics. Also, we can easily benchmark and compare data entries to evaluate reliability, right? I mean, you should understand that statistics is not timeless. Things can change from time to time. So when we compare past, present, and being able to forecast future data, we can actually benchmark and compare data results, right, to evaluate how reliable the data is and to comment on whether these changes are due to human error or if they are real world phenomenon that are actively changing these values and these conclusions that we can arrive at to better evaluate the certainty and reliability of the statistics. And also it helps to reduce dependence on individual effort to collect data, right? I think this is also very important. It's cost saving, right? Cost saving and also time efficient. I think it is extremely important because in terms of reducing the reliance on a single individual person, we can simply dedicate tasks to a group of people, and the tasks will often be completed more efficiently, more effectively, more accurately, and there isn't that form of stress being put on one single individual to collect data, whereas a body of people, a group of people can carry out these tasks. Descriptive and inferential statistics can help identify phenomenon in data sets without expensive tech or time-consuming long-term in-depth projects. So as you've said, we have descriptive and inferential statistics. When we use them hand in hand, we can actually identify phenomenon in data sets. And if in terms of having a short amount of time to complete such a task, and maybe we don't have a huge budget, using statistics, we can just collect data and we can identify phenomenon without having to use large, bulky, expensive technology or having to engage in very time-consuming tasks. So that is another possibility in terms of the advantages of statistics. And in terms of extrapolating trends, and we'll move on to regression lines in a little bit. Extrapolating trends is very important. It goes in hand with forecasting, and this is the most prevalent in finance when we are forecasting a company's success. Maybe that's their revenue, their profit. Right, investors use this all the time. So having statistics and being able to extrapolate trends to forecast the future is always very important, and it is crucial in many facets of our life. And finally, it can be easily extract information from large volumes of raw data, which can be challenging otherwise, right? So this goes in hand with not using expensive technology or time-consuming in-depth and long-term tasks. Being able to easily extract information from large volumes and through descriptive and inferential statistics is another advantage. Moving on to the disadvantages. Well, data is often collected, and we have already said this, it is often collected as numerical facts, so they're quantitative. So the lack of qualitative evidence, it can provide an incomplete outlook on a phenomenon, right? So not having that qualitative side, that descriptive side, sometimes it can be a disadvantage because we will not be able to fully grasp the complete outlook about why an event has taken place, or to be able to comment reliably on why something has happened. data might have uncertainties and or errors, right, which may lead to unprecise data. So sometimes statisticians, or even for us students, we might not actively realize that our statistics might have some uncertainties or errors, right? Or sometimes we assume and we do not comment about our assumptions, and this can all lead to unprecise data. The risk of misuse and misinterpretation are also two huge problems in terms of statistics, right? When what is being interpreted and what's being presented by the statistician themselves and how that statistic is being interpreted can be two individual ideas, and sometimes this could cause problems. And also the misuse of statistics can also be a red flag in terms of how reliable and how certain we can be with what is being extracted. The lack of homogeneity. So what homogeneity is, for example, you go to a restaurant, and this is in terms of a business point of view, you go to a restaurant and you pay for the service, right? For example, you pay for the service, you have the waitress or waiter that comes over and they serve you some food. Maybe you consume the food. Out of 10 times, you can tell, you can comment on how every single one of those 10 times the food may taste a little different, or the waitress or waiter treats you nice, maybe more nicer another day, maybe they're not as enthusiastic on another day, maybe, you know, so on and so forth. In sciences, we do many trials, so then we reduce that variability. We are able to comment on the overall result by taking, for example, the average, right, or conducting many trials and experiments. So the lack of homogeneity sometimes can actually lead to variability, and this can increase the level of uncertainty in terms of what we comment on about the data. It can also be challenging to decide between causation and dependence, right? As you're saying, when we're commenting on two or more observed characteristics, sometimes it can be challenging to decide whether something is a causation of another factor or if it's dependent on another factor or by pure chance, right? It can be challenging. So if this step, depending what is a causation and what is dependence, is not decided thoroughly and reasoned properly, then this can actually cause many problems. And we have seen companies this year and universities this year that have made statements that their vaccine is able to cure X amount of percentage of people that have tried it, and then some people say, oh, it's a causation, the vaccine is successful because the more people you test it on, or the success of the vaccine is dependent on how many people test it, well, as other people saying that, oh, the vaccine is good, so the causation is due to how effective the vaccine is, right? So there's that side of statistics where we have to make sure that we understand causation and dependence and to comment on it accordingly. Overgeneralizations can also cause problems, like cause complications in analysis, right? So generalizations is, once again, is that statement that we make about the conclusion of what we have found out in the statistics, and to gain the bigger picture behind statistics. And sometimes being able to generalize too much isn't a good thing, and this can cause a lack in clarity and also a lack of understanding, because sometimes we overgeneralize, and in fact, generalizing too much in some scenarios, it can cause assumptions to be made, and that could be an issue. And once again, assumptions may not be considered, which can lead to complications between observed phenomenon. So sometimes we make assumptions and the assumptions are not being considered or they're not being acknowledged, and this could definitely be a problem. And finally, samples may not be completely unbiased, and human error can lead to inaccurate data. So once again, as statisticians, we aim for our samples to be completely unbiased, but sometimes due to time constraints, or due to the ability of the statistician, it can be biased sometimes, and we might not acknowledge the human error, and this can all lead to inaccurate data. So that is something to definitely think about when we approach the use of statistics. We want to think about the advantages and the disadvantages. So moving on to the main ideas. So when we think about distributions, we think about the shape. And so what is a distribution? Well, colloquially, it is the overall skew, right? It's the overall skew of a graph. So when we think about the skew, we think about maybe if you're driving on the side of a mountain and the mountain is skewed one way, and so when you're driving, your car tilts in the direction of that tilt. So then you can think of skew kind of that tilt, right? That tilt in a graph, or where in terms of statistics, it is where most data is located. And this is this can be commented on when data is being visualized. So the most common that most students will be introduced to in terms of distribution is the Gaussian distribution, which is also acknowledged as the normal distribution, or more commonly known as the bell curve. So when we think of this, we can think of the bell curve as, for example, you have this x-axis, y-axis, right? So then your bell curve might look a little bit like that, right? So then you have your mean, so this is your mean, and this side goes up. So you can think of these two sides to be equal, right? These two sides to be of equal area, right? So if you take for example, the integral of this area, the integral of this area and the integral of that area will be the same. For example, integral initial is equal to integral final, right? For example, like that. Or integral left is equal to integral right, for example, right? So that would be an example of the Gaussian distribution. The second distribution will be the bimodal distribution or the multimodal distribution. And when you think of bimodal, you see the word bi, right? So the word bi should tell you that there's two, right? Bi is two. And multimodal is two or more. Let's just say maybe two approaches infinity, right? For example, so bimodal distribution could be something like this. So maybe you have one up here and then one up here. So then for that you have one and you have two humps. So this would be a bimodal distribution. And maybe for multimodal, you have something that looks a little like this. So one, two, three, four. So you have 1, 2, 3, 4. That would be a multimodal. Or maybe you only have 3, right? You have 3. That works too. Or maybe you have 5, right? So multimodal, anything that has 3 or more humps, or what you call it as maximums, that would be your multimodal distribution. A log normal distribution and an exponential normal. You think of exponential and log, well, even in a graph, you think exponential, it can simply go like this, right? It goes all the way up. That's like an exponential function, and a logarithmic function could go something like this, right? So then that could also be what you think about when you think about the distributions, right? It's simply the shape, right? In mathematics, this is simply the shape. So then this would be your log normal, since it's going from some very large value of y all the way down to y equals 0, right? That would be your log normal. And then your exponential could just go exponentially increase. You think about maybe the growth of bacteria in a culture of bacteria. The number of bacteria that are growing over time, it increases exponentially, right? You want to think of it that way, an exponential growth, right? So that could be something. That could be an exponential distribution. And it's also important to understand about the differences between continuous and discrete data. When you think about continuous, you want to think about continue, right? So what does that even mean? Well, continue, think about as data is being collected, there is an infinite measurement that is prone to change between observed variables. So for example, you measure the size of, for example, your pen with a ruler, right? There's always going to be some form of uncertainty. There's always going to be some form of human error. So maybe you will repeat and repeat and repeat, and maybe you measure the pen 5 times and it comes out to 7 centimeters, right? And maybe you say it's 7.1, sometimes you say it's 7.2, so maybe you say it's 7.12, right? But there's still uncertainty in that. So then maybe you can leave that as a continuous. You can measure that and leave it as a continuous data value, right? Because you're not completely sure. This could also be implemented into measuring the volume of water, right? Maybe you look at the water bottle and it is fully cylindrical, and you can measure the height, and you can just use pi r squared times height, and that will be your volume. And you find that the volume is about 60 centimeters cubed, right? But there's still uncertainty in that. So then you leave it as a continuous data point, right? So that could be a continuous data point. Or maybe you want to measure the rate at which water evaporates, and that as maybe a function of time. So maybe you heat a kettle of water and the water boils, and as water evaporates, you just measure every 10 minutes or every 2-3 minutes the new volume of water in the kettle, and that would be a continuous. Well, maybe at some moment of time in between 2 to 3 minutes, there isn't a specific time where the volume of water is 100% on that level, right? There's always going to be an error to it. So then you leave it as a continuous point. Whereas in discrete data points, it is more of the singular countable, it is countable, right? So it is singular countable object. So you can say there are 2 water bottles on my table, there are 3 airplanes. Well, there can't be 3.5 or 3 1/4 airplanes, or 1 3/4 of a person, right? There has to be a singular whole number associated to it. So discrete, it is that singular countable. So if anything, you can think of it as, for continuous data, you can think of this as measurable, and in terms of measurable, and then in terms of discrete data, you can think of it as countable, right? You have 2 planes, you have 3 people, right? Whereas in continuous, it is measurable. And from this, I have included 2 diagrams, so you can see that in continuous data, it is all in terms of a connected. There's all connectedness throughout. There is no individual points, right? Even for this temperature over time, you can see that this is, although it's not a straight line, it is not a linear line, it is still continuous. Whereas in discrete, we can see that this is a different reality. There are individual points. See, they're all individual points and they're not connected, right? See, there are individual points here, and there isn't a connection to all of it. And you can see, for example, tickets and cost, right? Tickets and cost. Well, you can't buy 1.5 tickets, right? Logically, you can't. If you're going to a movie theater and you have 2 people, you can't just buy 1.5. You have to buy either 1 ticket or 2 tickets, right? For savings a month, right? Maybe you're counting in terms of singular dollars, right? You can't have $1.5 in terms of bills, right? Let's just exclude cents for now, right? Savings, you have dollar bills, or maybe you say your $50 bills and you want to count how many $50 bills you can say. Well, you can't just rip a $50 bills in half and count that as 25, right? So then you have your individual points. That would be your savings over a month. So that's how you can think about the difference between continuous data and discrete data. And in other scenarios, this might be a challenge because we might not always be able to determine what is continuous and what is discrete. But think about it in that sense: continuous as measurable and discrete as countable. Now we move on to sampling methods. And sampling methods is something to note when, as a statistician, of course, because how are we always going to collect data? Are we always going to just survey everyone in our school, or survey people in our workplace? How do we know we can be unbiased, or how do we know what types of sampling methods are available? Well, there are multiple sampling methods. There are multiple methods to sample data, right? But the type that's being utilized depends on the purpose of the statistics, the importance of reliability and the accuracy, the available resources. So this might be the tech that is being used or the number of people that are involved in this data collection, as well as the time allocated and the audience of the statistic. So starting off, you have convenience sampling. And convenience, you think of it as convenience sampling, you think of it as convenience, of course, which is randomly selecting individuals nearby for the sake of convenience, right? So in this diagram that I've included, maybe you have one person here, you have another person here, and you have 1, 2, 3, 4, 5, 6 people, right? So then for the sake of convenience, maybe you just choose to have 3, right? Because they're convenience, they're closest to you. Maybe you're a person that is standing over here, right? And these are just maybe people that are nearby, but then you're like, okay, so I see these 3 people close here. I see this person, this person, this person. Well, they're close by, so let me just select those 3, right? That can be convenience sampling. You think of it in that sense. In terms of simple random sampling, well, this time it's a little different. It is selecting random subsets of individuals from a given group. Individual subsets just tells you that it is more of a segment, right? It's a segment of people in a given group. So maybe within these 6 people, you only want to select the person that is yellow, and out of you have red, pink, orange, purple, blue, and yellow. Those are the people. Maybe you choose the yellow person, right? So then you chose the yellow person, and so there's only one yellow here, right? That is simple random sampling. Next, you have your systematic sampling, and it is selecting an individual from a population after each predetermined interval, and is given by k equals to population divided by sample size, right? So a population, right? Although here there's only 6 people, and this is assuming that the population is 6, right? This population might be 10 million, might be 30 million, might be 1 billion, depending on how large the population of, for example, each country is. Or population might be the number of people in your family, or population might be the number of students in your school, for example, right? That could be a population. Then, for example, I have a population of 6 family members, and I want to only survey 3 people. So how do I know which people I should survey? Well, you use the formula. The interval for each person that you're choosing, the interval is going to be your sample size, right? You have your population divided by your sample size. So if you have a total of 6 for your population, and you only want to have a sample size of 3, then 6 divided by 3 is equal to 2. So for every second, right? For every second person, you select that person. So this would be, over here would be the first person. This would be the second person. So you would select this. This would be a third. This would be your fourth. You would select this person too. This would be your fifth. And this would be your sixth. And you would select this person too. So every second interval, you select this person. And here you will have your 3 people, which is also equal to your sample size. So this is your sample size here. This is your sample size, and this is your population. So that would be systematic sampling. Next, you have your stratified sampling, and this is selecting a proportion from a subset of a population such that the number of individuals are of equivalent ratio. Then the ratio is known as a strata. So for example, in a group, you can see that there are a total of 6 red people, there are a total of 2 orange people, and there are a total of 4 purple people, right? And your statistics says that you want to select only a half of each population. Well, if you want to select a half of each population, do you simply count the number of people in general and just divide it by half? Well, how do we know if that is fair? Well, of course it's not fair, because we know that these are different subsets of people. You have the red people, you have the orange people, and then finally you have the purple people, right? Obviously, this is not fair. So how do you make sure that you can divide the population by half in a fair and organized manner? Well, you can do this simply. How do you do it? Well, within each group, just take half of the people. So instead of having 6, you only take 3, right? Instead of taking 2, you just take 1. Instead of taking 4, you just take 2. So then this goes into your data sample. This would be your sample, right? As simple as that. That is stratified sampling. And finally, you have your quota sampling, which is selecting a predetermined size, a predetermined sample size of a population. So maybe a population, you only say, I need 4. So then you randomly just select 4 from the group, right? And that would be your quota sampling. Moving on to correlation and outliers. So if you said correlation, you can think of it as patterns, right? If you can find a pattern, you can comment on the correlation, a potential correlation. And an outlier, if you think of it in terms of an English phrase, you can say like, I am an outlier of society, or I'm an outlier in my friend group, right? You think of it as like something that is not supposed to be there, or something that is unusual, right? So with that being said, what is a correlation? Well, a correlation is when there is an observed relationship, trend, or pattern that manifests upon processing / extracting information from raw data. We determine the strength of correlation, or how certain we can be about a correlation, by calculating the correlation coefficient, denoted by the letter R, and the range is between -1 and 1. The range of r is between those two numbers, or those two integers, where the sign determines the direction of the regression line. As r approaches -1 or 1, the correlation becomes increasingly stronger. So what this means is that, for example, in a data space, right, in your graph, maybe you find that your overall graph, you have your data is going along something like this, right? Maybe you can say, I don't know, you're comparing x and some y, some x and some y, right? And for this, you find that a lot of your data points hover around this area. Well, then the line of best fit, and the line of best fit, recall that the line of best fit is just simply a line that goes through the data in the most equivalent way as possible, the most fair way, so then all the data points receive some proportion of the line. Your line of best fit will go through something like this, right? Some line like this. So then if r is between -1 and 1, you know that from simply linear functions, we know that if your slope, or m, equals 1, then simply this will go up. We know that m is also equal to rise over run. So then this will simply go up 1 to the right 1. So maybe here, up 1 to the right 1, here, up 1 to the right 1. So this would be your linear function, right? This would be slope of 1. And if this were, the slope were -1, then this would be the same, except it will be in the opposite direction, right? So with this, you can think of the range being the same, right? This basically explains why the range is between -1 and 1. So as the direction of, this is the sign, which is the negative in front, it determines whether if the direction of the regression line is positive or if it is negative, right? So that's what we want to think about. And as the correlation, or as r approaches to ±1, then the correlation becomes stronger, right? So with this, then if you think of a number line, if the correlation is between 1 and -1, this is strong and this is strong. So maybe strong, I can give it to as green, right? Maybe you think of green as good, so it's strong. And then as you approach to the middle, when there is 0, then this is a horrible correlation. Or you don't say horrible correlation, but you will say it's a weak correlation. Or in this case, if it's 0, there's no correlation. So maybe a graph that will show no correlation could be something like this. You have points all over the place and there is absolutely no correlation at all. So then your line of best fit, or your regression line, will look something like this. Simply go through the middle like this, right? And there is absolutely no slope on this. Why? Because there's no rise. And if there's no rise, then it is just simply 0 over run. And we know that when we do this, then this is just 0, right? Anything 0 divided by anything is just going to be 0. So if there's 0, then there is actually no correlation. So this would say that this is equivalent, or this represents no correlation. No correlation. Okay? So are there different types of correlation? Well, there are a few different types of correlation, but the most common one that most of us will learn in school will be the Pearson product moment coefficient correlation, or this is simply, thankfully, is just denoted by the letter R, right? You can find this on your graphing calculator. You'll find this in, for example, if you're taking an exam in your data bank, this will just be represented by R. And some other types of correlation may include the Kendall rank correlation, the Spearman correlation, and the Point-Bissell rule correlation. But these last three, they are not as common in high school, maybe in university courses, and for sure in real life applications, especially in the STEM fields. Those three other correlations may be used. But the most common one to use and to familiarize yourself with is the Pearson product moment coefficient correlation. This one is the one that you want to gain the most understanding about. So moving on to what are outliers. So as we've said, outliers are a range. So outliers are a range of raw data values. So it is actually a range of raw data values that must be omitted from calculation as they are outside the present accepted margin of error, and if they are considered, that this can impact the accuracy and reliability of results. So although your outlier will be presented as numbers, right? So they'll maybe you say your outliers, it can be some X and some Y. So your outliers can be those. So then anything that is past Y and anything that is lesser than X, they will be outliers. So they will be outliers. Right, I'll just put it as out, right? And we will do an example for that. But for example, in this example, anything that is past outliers, anything that's greater than maybe the outlier Y inclusive, and anything that is lesser than the outlier X inclusive will be considered as outliers. So moving on to an example, so you have the Pearson product moment coefficient correlation, right? Although the formula looks like it's huge and there's a lot going on with it, which I can agree, I think it is important to understand what they mean first. So you know that the first symbol, this backwards looking fancy E, is read as the summation or the summation of. And this is actually a Greek uppercase letter of sigma, and it represents the sum of, or the addition, right? X subscript I is read as X initial in physics, for example, but in mathematics you just say it's X initial, which represents any initial value of X, right? Any normal value of X. So whichever numbers you put on X, you will just read that as X. And it's the same as Y. Whichever maybe you have your X and Y values, your original value, not squared, not the square root of, not processed, just the normal value, the singular value, X or Y, with the subscript I, simply just says it's the initial value. X with a bar over it, this is read as X bar, or the mean, right? X bar is actually the mean, or in other words, it is the average of a sample data set. And N represents the total rows of data. So in this data set, for example, you have your first row here. You have or not row, but column. You have your second column here. You have your third column here. And you have your fourth column here. For that, N would be equal to 4. Right? So that is, N represents the rows of data, or you can think of it as the pair of XY pairs in the data set. So with that being said, there are actually two formulas. You think of it as R is equal to all of this, or R is equal to this. But you need to also understand that these all have different formulas too. So this might be counterintuitive, but if you want to think of it as the first one, go ahead, right? But you have to do a lot of addition and also multiply it. So if you're more of if you think that you're up for a challenge of multiplying and a lot more processing of data, you can go for the first one. Or I like to go with the second one more, even though we see that there's a lot more formula, right? But let's get into a real example, an example that I made up. And this example, what this shows is I've collected data on how much time I've spent to practice on a game per week. And this is the time spent per day for a week. And the earnings that I've gained from maybe a weekend tournament on that week, right? So maybe Monday and Friday, I practice 1 hour each day. And on Saturday and Sunday, during a tournament, I earn $10. And then the next week, I practice for 4 hours, right? And then my earnings are $30, 8 hours for a week. And then on weekends, I earn $100. And maybe on the fourth week, I spend 10 hours a day to practice and I only earn $90, right? So if I'm using the second formula, right, R, or the Pearson product moment coefficient correlation, is equal to S subscript XY divided by the root of the product S subscript XX S subscript YY. So then I can just input what S subscript XY and all the others into this. So then I get this huge formula here, okay? So I'll just read this through once in case you want to know how it's being read. So this is simply R equals to the summation of xy minus the equation summation x summation y over n divided by the root of the product summation x squared minus the equation summation x all squared divided by n multiplied by summation y squared minus the equation summation y all squared divided by n, right? So this is simply plugging in what s subscript xy is, s subscript xx, s subscript yy, all into this equation. And so how do we get this? How do we get these numbers over here, right? Do we just randomly plug it in? Well, of course not, right? This is where this comes in, okay? So when we think about summation, right? When we think about summation, we look at summation. Summation x simply means that you're adding all the x values. You're just adding them up, right? When you think of 8 hours, right? 8 hours is simply just add the numbers up. You don't worry about 8 hours, 8 cubic meters, 8 cubic centimeters, something like that. You just add the numbers up. So then you have 1 plus 4 plus 8 plus 10. That's equal to 23, okay? Then you have your summation y, which is the same idea. You're just adding 10, 30, 100, and 90. So 10, 30, 190, you get 230. Summation x squared. So now you see that I added the brackets, right? I added the brackets in because it's summation x squared. So whenever you see something like this, you don't want to just say summation x and then you square. You want to think about the summation of x squared, okay? So you square the x first and then you add them up together. So you have 1 squared, 4 squared, 8 squared, and then 10 squared, right? So then all those x values squared, you get 116, 64, 100, so you get 181, and you do that for y. So then you square 10, square 30, square 100, square 90, and then you get this number, 19,100. And then xy, once again, you don't want to sum up the x and multiply by y. You want to think of it as summation, the summation of xy. So then you multiply x and y together. So then this time, you want to multiply 1 and 10. You want to multiply 4 and 30. You want to multiply 8 and 100. You want to multiply 90 and 10. And then once you have done that, you want to simply just add them together and get 1,830. And once again, n is equal to 4, as we have said before. This is your first column here. This is your second column here. This is your third. And finally, you have your fourth. So since there are 4 columns, then your n will be equal to 4, okay? So after you have this down, you have collected all your data, and you've processed them using this formula, well, then you just plug them in. Whenever there is a summation x, summation y, you simply just plug in each individual value into the formula. And once you're done, you get a fraction, of course, and you divide the fraction out, you leave it to 2 significant figures. Usually you would do it to 2 significant figures, right? And you get that r is approximately equal to 0.95. And since we said that then that number line, you go from -1 here, and then you have 1, and then you have 0, right? And here this is no correlation, so no correlation. So 0.95 is around here, right? And here we say that this is a perfect correlation. So a perfect correlation. And same as for 1, this is also a perfect negative correlation, right? Perfect correlation. So if this is 0.95, then we know that we are very close to a perfect correlation. So then we can say this is a very strong positive correlation. So since it's a very strong positive correlation, what does this all mean? What does the correlation mean? Well, since this is a positive correlation, we know that this will look something like this, right? Something like that. This might be time spent, and this will be your earnings. So the more time you spend, as t increases, y increases. So what does this mean? Well, this tells you that, for example, the more time you spend practicing a game, the more money you earn at the end of the week, right? That's what it all means. That's why we do this correlation coefficient, why we calculate R. We calculate R so we're able to see what is correlation coefficient, right? In the past, we just see a line and we're saying, okay, well, maybe it is this steep, maybe it is super steep, right? How do we know which one it is? Well, there's a now we can actually find out that value for R. We can now comment on whether if how strong or the strength of the correlation, right? We want to know how strong it is, and now we're able to find that using the Pearson product moment coefficient correlation, right? So that is an example. Moving on to how to calculate outliers. So outliers, to find outliers, we first need to determine the data set's upper quartile and lower quartile. And the upper quartile and lower quartile is given is being denoted by Q3 and Q1. So some of you may question, well, where's Q2 then? Well, this is a brilliant question. Q2 is simply your median, right? So Q2 is simply your median. The median of your data set, right? It's the median. And once again, recall that the median is simply the center of a data set. So for example, you have a data set here, you have x1, x2, x3, right? For example, these are commas. Then your median is just going to be the center because you have one to the left and then you have one to the right in terms of the numbers. So then your center is the median, right? So your Q3 has something to also do with the median, right? And you'll see this shortly. So given this data set, you have 1, 4, 6, 7, 8, 10, 19, 32. What's the first thing we do? Well, we check whether if these numbers go from lowest number to highest number. So the number should be placed in ascending order first. And this is very, very, very important, right? Because if we don't, the center number might be, the center number will always be either the one number or the two numbers in the center. But then the median will change because the digit that is taking up the space in the median, where the median is supposed to be, is changed. So then your median will also change. So you have to make sure to order your numbers in ascending order, okay? So how do we find the upper quartile? Well, to find the upper quartile, we first need to think about what that means. We think of upper as up, right? What does that all mean? Well, that just means anything that is higher. Anything that is higher than your median. And your lower quartile, well, lower is just below or lower. So you can think of anything that's lower than your median. And so obviously this would be your median. This would symbolize your data set's median, right? Because you have one number here, one number here, one number here. So there's a total of 3 numbers to the right of the median. So then you have 3 numbers to the left of your median. So these 2 numbers in the middle would be your median. So your upper quartile, right? Same idea. In order to find the median of this data set, well, how do we know whether if the median is 7 or 8? If we can't find out, what do we do? Well, you got it. It's just finding the average. So this is simply 7 plus 8 divided by 2, which is also equal to 15 divided by 2, which is also equal to 7.5, which you could probably already guess because the difference between 7 and 8 is only 1, so you divide by 2, it's just 0.5, and you add on to the 7, so 7.5 is your median, right? Your median is 7.5. So since we have 3 values here, we don't have to do the same thing. We can simply take the center value, and that would be your upper quartile, and we take the center value, and that would be your lower quartile. And there you have it. So Q1 equals to 4, and Q3 equals to 19. So then this would represent Q2. So with this information, what do we do with it? What does knowing upper quartile, lower quartile, what does that even tell us? Well, now we use these pieces of information to calculate our interquartile range, or our IQR. And your interquartile range, luckily enough, is simply your upper quartile minus your lower quartile. In this case, 19 minus 4, and you get 15. So then after you know your interquartile range, your IQR is equal to 15, then all we have to do now is this final step, which is knowing that these two formulas, right? Q3 plus 1.5 times IQR and Q1 minus 1.5 times IQR. So you think of this as like a confidence interval, right? How confident you can be of something. We multiply it by an error margin of 1.5 because that gives us an additional error margin of 50%. 1.5 as a percentage is simply 150%, right? It's also 150%. So having this 150%, this gives us an error margin. So an error margin of 50%, right? And that is universally, statisticians created this error margin of 50%. So then you think of why do we add here and why do we subtract here, and how do I just simply guess it and hopefully I get it right? There's a 50%, right? This is a statistical joke. But anyways, how do we know which one to add and which one to subtract? Well, you think of it as, for example, on once again a number line, right? You have your you have most of your values here. Your values, this is your range, okay? For example, this is your range. This is your range right here, right? So what is this area here, right? This area outside of this. What is this here? Well, that out here, is that your outlier? Well, we don't know, right? This simply, what it is saying how far we can push this out to still be sure that we can include that as a point. We know that the data values hover within this area, okay? But how do we know? Do we know that anything outside of this is simply an outlier? Well, we don't know, right? So what we want to do is that we give it a 50% error margin so that we can push the values out a little bit. So it's saying that if there are values that are being found from here to here, we can still include them. If we have any values that are found from here to here, we can still include them, right? That is basically what it's saying. And since we're subtracting 1.5 times IQR, we're subtracting our interquartile range, then what we are really doing is saying, even if values hover outside of this active area, we can still be confident enough to add them in our calculation. That is what it basically is about. So if we take our upper quartile and we add the error margin, then we are actively pushing this out and saying that any values that hover beyond this we can still include because we're still confident that it's still within the present error margin. And anything that is less than our lower quartile, we can still include them because we're confident that we can include them in because it's still within our present error margin. So within this, and I know it's really messy this one, I'll erase all of this, but just keep in mind if you need to pause this video and go back and look at what I was explaining about or even any questions, do leave them in the comments. But I hope that was a good elaboration on what or how we can remember when to add and when to subtract. We are basically extending it past, saying that if there are any values that are past our upper quartile or any values that are below our lower quartile, we can still include them in the calculation because it is still under that 50% error margin. But after doing this calculation, right, we arrive at two values, 41.5 and negative 18.5. And since we know that, for example, on this number line, right, if we were to input our values, maybe this is 1, 4, 6, 7, 8, 10, 19, 32, for example, not drawn to scale, right? We have these values over here. Then it's saying that all the way, or maybe I should draw a dotted line to show, all the way back here, there's some point over here that is negative 18.5, right? All the way back here. And since we know this is the final outlier, any values that are here to here, we can still include them because we're still confident that we can. This just symbolizes that it's not filled in, so it does not include negative 18.5. So maybe we take another calculation and we get negative 18. Maybe without finding the outliers, we'll say, oh my goodness, negative 18 and then 1, 4, 6. We can obviously not include that because it is already part of an outlier, but in fact it is still within. Negative 18 is about right here, so we can still include it, right? And over here this extends out a little bit more, all the way till maybe here. And this is some point 41.5, right? This some point 41.5, if we get 40, we can still include it, right? We get 41.5 over here, which means any values that are past here, we can still include them, right? Any values that are past this all the way to here, we can still include them. If you get 41, it's all over here, right? 41, for example, we can still include it. It still works, right? It's still within our outlier. So that's basically what outliers are. Moving on to scatter plots and histograms. So think of scatter plots and histograms as just two ways of presenting data, right? It's two ways of visualizing data. But what is most important, and what's the first thing you should look at, is what types of data? Well, remember how we said continuous? We have connected points that are not individual values. Well, that's what we use in histograms. Realize the difference between the histogram. The difference between a histogram and a bar chart or a bar graph is that there are no spaces between a histogram. Why are there no spaces between a histogram? Because they're continuous. They're continuous. I mean, we continue something, there are no breaks, there are no gaps in between, right? So then that's why we use histograms, to represent data that is continuous, right? And to visualize the frequency of an observed variable against another variable. Unlike a bar graph, there are no gaps in between, right? And instead of using the Pearson correlation, or R, we can simply comment on the skew. The skew will help us determine the overall distribution of the numerical data. So colloquially, this is basically where the majority of the data is present. So for example, in this graph here, we might realize that this is the overall shape that it takes, right? So you can say that most of the data points they are between here and here, right? But more data is over here because this is slightly higher, but there's also data over here, right? So this is a bimodal distribution. As we have said, bimodal, there are two modes, there are two maximums. So then this would be a bimodal distribution. This would be a skew left. A skew left because you can see most of for example, this is the middle. There's more data, there's a huge amount of data that is on the right side, right? So you do say that this is negatively skewed. Why is it negatively skewed? Because there's less data. There's less data on the left side. Whereas this is positively skewed. There's less data on the positive side. This is the negative side, right? And think of this as the middle, right? And this is positive and this is negative, right? So there's more data on the negative side. So we say this is positively skewed, whereas this is negatively skewed. So is this skewed at all? Well, there's no skewage in this, right? Maybe a little to the left, just because there's one extra, it's a little higher on the left side. But overall, this is what you call a normal distribution. A normal distribution usually does not have a skew. A normal or a unimodal distribution, right? They even add here that it is symmetric, but this is a normal distribution, right? Or a Gaussian distribution. So this would be no skew, right? And this is uniform because most of the data kind of goes like this, kind of goes across, right? So this is uniform. Whereas scatter plots, you can see that they're individual points, and this is an outlier here. They include that it's an outlier, but most of the points are individual. So where's the actual line of best fit? Well, the line of best fit, according to this graph, kind of goes around like this, right? And they call it the trend line, but this is really the line of best fit. The trend line is also the same as the line of best fit, but the trend line just tells you what's the trend of all the data, right? Independent variable, dependent variable. You have the trend line going in this positive direction, okay? So what are scatter plots? Well, scatter plots are used for discrete data. This time we have discrete. We're dealing with discrete data. It's used to compare two variables, which located on the x and the y axis. This is used to determine if there is a trend and the strength of the trend. Well, in this case, we would use the Pearson product moment coefficient correlation, right? And we lead back to R, where R is such that R is greater or equal to -1, lesser or equal to 1, and R is an element of all real numbers. and the correlation is strongest as R approaches positive or negative 1. So this is just a little review of what histograms and scatter plots are. Moving on to cumulative frequency. So what is the cumulative frequency? Well, cumulative frequency is the sum of frequency of the data values within a data set for both discrete and continuous data. The only difference is how they're being presented, as an integer or a range of values, right? So you want to think about cumulative frequency, you want to think about cumulative, right? Cumulative, you can say accumulate. Accumulate is just adding, right? So you keep adding the frequencies, okay? So for example, in this example, this data set over here, it's a representation of the marks scored on IB higher level mathematics quiz where the test is out of 10. These individual points over here, these individual values, they represent test scores. And for each individual value, that represents a student that has gotten that score. So maybe there's one student that gets a 1, there are two students that get a 3, there's 2 students that get a 4, there are a total of 4 students that get a 5, 2 students get a 7, 2 students get an 8, 1 student get a 9, and 1 student get a 10. Okay, so that is how we would interpret this. So we know that there are a total of 15 students, and there are a total of 15 data points, and we have just elaborated that each data point or each value after a comma precedes a comma is a student. But we can also represent this another way. So we know that there's the marks here. We know that there's a student. So then what does the cumulative frequency matter? Well, cumulative frequency is most often used to comment on the percentile of something, right? When people say, oh, you are the 90th percentile, you are the 99th percentile, that means that you're that top 1%, right? So when we're saying cumulative frequency, we want to add the frequency, right? But you have to determine what is the frequency they're adding, right? In this case, we're adding the frequency of the students. So when we have one mark, there's one student, you get a cumulative frequency of 1. When we go on to students that have scored 3 marks, there are a total of 2 students that get it, but we get a cumulative frequency of 3. And you can kind of see how this works. You have 1 plus 2, and this equals 3. So then this goes here, right? For your third row, you have a total of 4 marks, right? I'm going to change it in a different color, 4 marks. And now you have another 2 students that get 4 marks, but then you have a number 5 now. So how do you get that? Well, you can think of it as this way. 1 plus 2 plus 2, that equals 5. So you can kind of see a pattern now, right? On the very bottom, when there's a 15, we know that one student gets a 15, but why is the cumulative frequency of 15? Well, you're adding this entire section, and this equals to 15. So every single time you want to have a cumulative frequency, you're basically adding the frequencies, right? As we have said, we are adding the frequencies as we're going down. And realize that the cumulative frequency at the end, it's the same as the number of students. Why? Because the original frequency is the number of students. The original frequency is the number of students, right? So at the end, you will have your cumulative frequency equal to the number of students, which is your original frequency. Using this same graph, we can also graph this, right? Using this table, we can actually graph this relationship. So notice that the cumulative frequency is the sum of each successive row of frequency. And your final row is the sum of all successive frequencies, which is also the total number of data points. And we can graph this relationship. So as we've just discussed, and now for this, notice that there is a 1, right? On the bottom, there's a score of 1, and you can see that this is the score and this is the number of students. We have a score of 1 and we get 1 person. We have a score of 3 and we get a total of 3 people. What does this 3 actually symbolize though? Well, this 3 symbolizes that between scores 1 and scores 3, there are a total of 3 people that have scored between these two, right? Moving on to 4. Why do we have a 5 here? Well, it's basically saying that between students that have scored a total of 1 all the way to 5, there are a total of 4 students that have done so, right? So students that have scored from 1 to 4, there's a total students that have scored is 5 of them. And we can see this up here too, right? We know that for this, students that scored marks 1, 3, and 4 is simply as 1 plus 2 plus 2, and this 3 equals to 5. And we have gotten a 5 here, right? So at the very, very end, right? At the very, very end, we have a 10. We know that not 15 students scored 10s, but we know that we can find out how many students scored a 10 by taking the difference between these two. Whenever you want to find out how many, or whether if it's the number of students or any observed variable that you're trying to find, if you want to find out what's the last value, always take the difference with the value that was before it. So for this, you have the cumulative frequency of 15 and 14, then you know that 15 minus 14 is equal to 1. If you want to find out how many students scored, for example, a 7, you take the difference between 9 and 11, and you know that this equals a 2. And when you look at 7, indeed it is 2. So this is also another way that cumulative frequency graphs can be helpful. And as I've written here, this is a cumulative frequency graph. Observe how the scores are on the x-axis, the number of students are on the y-axis, and you have to make the decision on which is an independent variable and what is a dependent variable. And for this specific scenario, I have shown how the mark is an independent variable and the number of students is a dependent variable, because I'm saying that the scores don't depend on the number of students, right? So if it doesn't depend on the number of students, then it is an independent variable. And then the other variable is, of course, the dependent variable. Moving on to standard deviation and variance. So what is standard deviation? Well, standard deviation, which is denoted by the two letters SD, is then denoted by the lowercase Greek letter sigma, right? So remember that the uppercase sigma was this, and now you have lowercase sigma, which is that, right? And this measures the dispersion of data values within a data set for both a sample and population, right? So for this, the dispersion is the spread. It is the spread of data with respect to the mean of the data set. In other words, it is the measure to determine the quartile that the data value or values deviate from the mean. Okay, so when you want to measure the dispersion, you're saying that, for example, this is the center, right? This is the central tendency. This is where most data is found. So if you find a data that's out here, for example, what's the distance? So like, what is the spread between this and here? That is basically standard deviation. And how do we calculate this? Well, we calculate this using standard deviations, right? We have 1 standard deviation, 2 standard deviation, 3 standard deviations, and then we have the equivalent counterpart, except it is in the negative direction. So that is what standard deviation is, right? We want to find out what is the deviation from the mean, in the middle, right? That is basically what standard deviation is. So it is also important to understand that when we have standard deviations, we have the middle, which is the mean. And since this is written in the Greek letter mu, then this would be a population data. Whereas if it is written as a sample data space, then this would simply be x with a bar over it, or x bar, and this would represent sample, right? Sample. But this over here, this is mu, and this would actually represent population. Okay, population. So since this is mu, then what does this 1 standard deviation mean? And what's this -1 standard deviation? Well, we're trying to say that any values between the mean and the standard deviation, 1 standard deviation, it's about 34.1%. So any values that are between -1 standard deviation and 1 standard deviation is simply 34.1% times 2. So most data values are between these two, right? You can see that between if x, for example, x is greater or equal to -1 standard deviations and is lesser or equal to 1 standard deviation, then the data between these 2 points is approximately 68.2%. Okay, so most data is found between here, about 68.2%. And if you go from 1 standard deviation to 2 standard deviation, then there's an additional 13.6%. And 13.6%, you go from -1 standard deviation to -2 standard deviations. And as you can see, the more standard deviations you go out, the lesser percentage of data can be found there. So most data is found between 1 standard deviation and -1 standard deviation. So how do we calculate what is 1 standard deviation? Well, we calculate 1 standard deviation by using one of these 2 formulas. And one of these 2 formulas, there are 2 different types. There's one for sample and there's one for population. As we have seen, for population, it uses mu. And as you see in sample, it uses x bar. So standard deviation is equal to the square root of the summation of the product x minus x bar all squared divided by n minus 1, where x bar means the mean of the sample and n is equal to the number of data values in the sample. In population, this is very similar, almost identical, except there is no n minus 1. It is simply just n, and the n represents the number of data values in the population. Now, what is variance, right? Well, variance is simply denoted by s squared, or it's also standard deviation squared. Variance is simply standard deviation squared. So if you want to find a variance, simply take, and you're working either with a population or you're working with sample data, simply take standard deviation and square it. Standard deviation and square it. And what do you see? Well, what should be obvious almost is that if you square standard deviation for sample or population, it's simply just erasing away your square root. So it's simply just erasing away your square root. So you don't actually have a square root anymore, just what's inside. So if you find a variance, you want to find a variance, you just take what's inside here, right? You just care about what's inside here. If you were to take the variance, standard deviation helps you to find out what is the deviation away from the mean. And then if you're finding the variance, it's just taking away the square root, and it's just standard deviation squared. So then from that is basically the difference between standard deviation and variance, and what variance is. In terms of the use of variance, you don't really use variance in, I would say, high school mathematics a lot, but in other occupations, maybe in finance, right? In finance, standard deviation and variance, maybe variance will be used in finance, is used to calculate the square of the standard deviation in a data set. So maybe instead of finding what's the standard deviation, right? Instead of finding, oh, the standard deviation here, you want to find the square of it. You want to find the square of it. So then this would be your variance, because if you're taking standard deviation squared, it's simply like this and this. This is your standard deviation. This is your standard deviation, and then basically you're squaring it. So then this area in between would actually, this would be your variance. Ensure that you understand the concept of standard deviation and understand some potential implications of variance, especially in finance. Moving on to the Box-and-Whisker plot. So what is a Box-and-Whisker plot? Well, in short, it is another method of visualizing data, right? The Box-and-Whisker plot is used to visualize the skew of a dataset. It does so by presenting a wide range of information. It presents the mean, the upper and lower quartiles, once again Q1, Q3, as well as the maximum and the minimum, as well as outliers. So for instance, in this particular dataset, I've stated that the mean is 10, the maximum is 100, the minimum is 0, upper quartile is 92, and the lower quartile is 3. So we can simply just plug this in, right? We can make a data set. This is where the minimum value in your data set is, which is 0. This is your maximum value in your data set, which is 100. You have your upper quartile at 92, your lower quartile at 3, and well, make sure that just be sure to understand that this diagram is not drawn to scale. It's just simply for demonstration purposes. And this X bar, which is your mean, your sample mean to be specific, is 10. So having this Box-and-Whisker plot, why did we call it Box-and-Whisker plot? Well, this outside part is kind of like a box, right? And whoever decided to name this as a whisker, well, that's how we kind of name it as the Box-and-Whisker plot. That's basically what it is, and it's another way to show the skew of the data, right? So if we were to comment on the skew of this, well, we can say that most data is kind of like this, right? There isn't really a skew to this, right? 92 is only 8 away from 100, and 0 and 3, this is, well, just 3. So we can say maybe there's more data on this side, just a tad bit, just a little bit more data here. So we can say maybe it is negatively skewed. There's more data. Let's say maybe it's more data here. Okay, so maybe there's more data here. So that's how we can also determine the skew of a data set using the Box-and-Whisker plot. Something that's important to note, however, is that we must not assume that outliers simply lie outside the maximum or minimum. Instead, we must find the outliers, and we have explained that just now, because not every single time your maximum and your minimum will be your outlier, right? We want to find out to what extent can we extend the margin of error here. We can extend this area in between, even though it's past the maximum, to allocate space to include other values that may take up space from here all the way to here. And anything that's past here is an outlier. For example, this would be an outlier, and this over here would still be okay, right? So once again, we plug in Q3 plus 1.5 times IQR and Q1 minus 1.5 times IQR. You find the numbers are between 213.5 and negative 118.5. So as long as the values there are no values that are greater than 213.5 or equal, there should be an equal sign here, because if it's equal to, it will still be an outlier. So as long as values are not greater or equal to 213.5 or not less or equal to negative 118.5, then there are no outliers in this example. So finally, we have additional reading material, and as I've said at the beginning, these are not necessary, but I do encourage you to give them a read or conduct some level of research to just understand a little more about these topics, because I find them very interesting. And yes, they're more complex, but as we grow older, we will understand the importance of these different subtopics that I find are definitely interesting and important for us to grasp. So some include the null hypothesis, the z-test, and the t-test. Hypotheses in statistics are very important. It is used to disprove whether if something is true or not. General linear model, analysis of variance, so you'll learn about more ways to use variance and to how to analyze them. Stem and leaf diagram or stem plot. I chose not to include this into today's lesson because it's a very small component, and it's just another way of, it's almost like used to save space, right? In terms of writing down data in such a way, instead of writing them in a data set, you just choose to use a stem and leaf diagram. So if you would like to look up how that is used, it is pretty easy to use, but it is not a very crucial thing to use. Most people will list the data out as a set. But if you would like to learn more about the stem and leaf diagram or stem plot, go ahead. The analysis of covariance, so another new idea, covariance. Confidence interval, which is just tied into null hypotheses. Binomial theorem is used in many facets of mathematics, but if you like to know the implications of binomial theorem in statistics, go ahead. Piecewise functions are also introduced in, I think, linear algebra and also in calculus. But if you like to learn more about piecewise functions in terms of statistics, I would encourage you to do so. And finally, the difference between x on y and y on x regression. I've just introduced x on y regression, but there's also y on x regression, which is instead of having your x and your y, you actually flip the two, and usually it will come up with a different equation, and you'll be able to find out what are the difference between x on y and y on x regression. But that is for you to find out if you would like to gain more insight into the topic. But yeah, those are some topics that I would encourage viewers to pay attention to look out for, and to expand your horizon on what statistics can involve. And thank you guys so much for watching this video on statistics. I hope you guys have found this video particularly helpful. If you guys are new to the subject, I hope I have been able to expand your horizon a little bit on the topic of statistics. And if there are any suggestions or you have any ideas for future videos, please do leave them in the comment section. If you feel that this video can be helped to a friend or a family member, please do share this video. I hope that you had a good time watching this, and I hope you enjoyed. It's been Stefan. Take care, and I'll see you in the next video. Peace out, everyone.